Hello, good evening, good afternoon, good morning, everybody. My name is Andreas Riedel, and I'm your host and your presenter of today's online seminar. This is part 5 of an Atlas series of fundamentals of weathering online seminars. Thank you very much for being here today, for attending virtually. And the topic of today is acceleration. Before I start with introducing myself and the company and going into the topic, a few housekeeping items here. This presentation will be 1 hour. We will distribute it via a link after the online seminar. If you have questions, please feel free to type the question or the questions into the box that you see in your control panel. I will address your questions at the end of the session. I will try to conclude a couple of minutes earlier, depending on how many questions are coming in. If you have follow-up questions, which always is welcome, please go to our website and click on the Contact Us button on one of our websites. We have it in different languages. Click on the Contact Us button, type in your request, suggestion, recommendation, or question, and somebody will come back to you, somebody who speaks your language, and somebody who is located in the area that you are from. Also, check out our online seminar calendar for other topics that may be of interest for you. I have put the URL down here. You don't have to write that. You will get the presentation anyway. All right, now a few words to myself and to the company for those of you who do not know Atlas well. My name is Andreas Riedel. As I told you before, you may have realized from my very strong accent that I am not an English native speaker. I'm a German. My background is in physics, biology, and chemistry. I have about 30 years experience in material and product performance testing, standardization, test method development. Before I joined Atlas in 1999, I worked for the industry association of caravans and motor caravans and was director of technical and environmental affairs back then, also dealing with ISO and CEN and DIN and ASTM standards. I'm chairman of the SKZ Symposium on Weathering of Plastics and session chair at European Weathering Symposium or GUS conferences sometimes, if time allows. Our company, Atlas Material Testing Technology, has quite a long history. We have been around for much more than 100 years. Our specialty is weathering, and we are the market and technology leader in weathering instruments. We also have a line of corrosion instruments. Our laboratory services and outdoor services are frequently used all around the world. We have sites, a big network of testing sites. One of our activities also deals with custom-made solar simulators, scalable. The picture below here on the left, it shows a huge solar simulator where you can put a train or car or even a fighter plane under to investigate solar load. Similar kinds of light sources are also used for high-speed lighting and technical lighting purposes, and we are producing those custom-made systems as well. Last but not least, we are quite active in standardization, committee representation. We are also having a very, let's say, advanced program of client education seminars for beginners, but also for advanced people up to scientific level. And we also provide consulting to our customers, especially with regard to applications and to test method development. So this should do it. That was the commercial. 5 minutes into today's presentation, the right time to start. We are in part 5 right now of the series of fundamentals of weathering. Just for your overview, you should know that there are other parts, 1, 2, 3, 4, and part 6 as well. It is not mandatory that you listen to all these parts in this order. So you can go into the outdoor weathering next, or factors of weathering, and then correlation, then test methods. So the order is not important. You should listen to those classes whenever your calendar allows. All right, today it's acceleration time. This is the outline of today's slides. Acceleration factor will be the first, then examples for acceleration factors. I will talk a little bit about time compression and a little bit more in depth about intensification of specific weathering parameters to achieve higher acceleration. And I will end with a summary. A common question for everybody dealing with weathering is, what is the acceleration between my laboratory xenon test and static auto exposure? As you may have heard either myself or one of my ATLAS colleagues say before, this is without any doubt the most often asked question we get, literally on almost a daily basis. The question is often worded to be more specific as how many hours in my weatherometer equals a year in Florida, or in Chennai, or in Sunbury, or in Phoenix, Arizona. Even though you are all muted right now, I can imagine the nodding of heads and all of you saying, yes, that's what I want to know, and expect me to give you the magic number. The second most asked question then is always, or at least should be, what or how good is the correlation between these exposures, laboratory to field or laboratory to outdoors? But actually, this last question should come first, because high test acceleration, while desirable, is meaningless if the results don't correlate. I hope you agree. So fast test with bad results is useless. But what information can we use to potentially predict test acceleration beforehand, which we often need to estimate a test duration? Well, starting point maybe to compare the cumulative radiant exposure. Some call that dose or dosage. I don't like that because that is coming from other fields like medical science or radioactivity, and is usually used for absorbed radiation. So let's stay with the right term, radiant exposure, for a target auto location to that same radiant exposure in our laboratory test. The comparison of these two. Here's an example. How long should I test in a weatherometer to simulate 1 year of exposure at the ATLAS test site in Chennai, India? Well, we know how much radiant energy we receive at this location, and I put that here. It is 400 megajoule per square meter per year on average. Now let's say that we are running a laboratory test in a xenon arc instrument following method A of ISO 4892 part 2. And this is 60 watt per square meter using an outdoor daylight filter set without dark phase. Rain is included, but no dark phase. So we have 60 watt per square meter in the instrument and 400 megajoule per square meter to achieve. How long does it take? It's quite a very easy and quick calculation. I will guide you through that. We start, oops, is it? Aha. So we have the annual radiant exposure in Chennai, 400 megajoule per square meter. We have the irradiance of the laboratory instrument of 60 watt per square meter. And the formula is radiant exposure is irradiance times time. watt per square meter times hours, it's watt hours or watt seconds, which is joule watt seconds, and this is the radiant exposure. There's the formula again. We change it to have the time here, which is radiant exposure divided by irradiance. I choose the values because they are easy to calculate without a calculator. 400 megajoule per square meter divided by 60 watt per square meter. A watt is a joule per second. So a joule per watt is a second. It's very easy. It's 400 divided by 60, which is 6.7 megaseconds, million seconds, 10 to the 6th, which is 11 weeks. And then the acceleration factor is 11 weeks divided by 52 weeks, because a year in Chennai, and by the way, everywhere else, is 52 weeks. And this leads to the acceleration factor with an index E, meaning irradiance, only of 4.7. So now let's go back to the red disclaimer that I had put down here. This is only a rough estimate based on radiation only. What we neglect is temperature, relative humidity, rain, and all secondary weather factors as well. And the most important neglected property here is the material response to the weather factors. So we are calculating acceleration factors only based on weather data. Acceleration factors should always be calculated or determined, not calculated, determined by looking at the material response, right? So this is very important to know what we just did. It's a very rough estimate that I calculated here in this short calculation. Some of our colleagues say, Andreas, don't show that. We shouldn't talk about that. We should, not misguide people to do these calculations. I think it is good that you see that, but that you get the full disclaimers, the full cautions, the full explanation what's behind it. It's only a rough estimate. It doesn't include any material property, any temperature, any rain and humidity. All right, so what is an acceleration factor then? In general, we have the blue curve here, which is a property change over time. X-axis is time. After a certain time in field, the pass-fail criteria is met. This is characterized by this red line, and this is then called service life. If we have a faster test, which doesn't distort the mechanisms, we reach that service life after a shorter time because it's a faster test, it's an accelerated test. And these two times divided by each other is the acceleration factor. It's as easy as that. It's very, very easy, very simple. The definition is very simple, but what's behind it is very complex. In all accelerated testing, not just weathering, we have only two possibilities for test acceleration. The first of these is time compression. The second is intensification. And here are the definitions of a German VDI, that's Association of German Engineers, standard 3958, page 1. These are the two definitions. In English, usually you don't deal with time compression. It's all called acceleration. But in German language, we differentiate. And there is a reason why we differentiate. You will see very soon. So let's look at the time compression. How do we achieve it? For most traditional laboratory weathering test methods with artificial light sources, such as the common ASTM, ISO, or SAE methods, the irradiance level is either at or even below the maximum solar intensity you would see during peak auto exposures. such as summer noontime. But of course, in the laboratory, we can run at these conditions continuously and just delete the dark night times. You see that? And then we have the same integral here, which is the radiant exposure, because this is the irradiance and this is the time. I just told you that irradiance integrated over a time is the radiant exposure. And then we get to this same integral here, but in a shorter time. And this is called time compression. So the compressed test, the time to reach a specific radiant exposure is much shorter than outdoors. That's the whole trick. Many basic test standards specify typical maximum values for the key testing parameters. For example, the 60 watt per square meter, which I just used in my quick calculation, is a typical maximum natural noon irradiance. 65 Celsius is a maximum temperature frequently occurring at noon in extreme climates such as Phoenix or Chennai. Measurement data of all these values and how they are derived and how the test methods are derived from the real world data. This is dealt with in other parts of that fundamentals of weathering series, in the outdoor part and also in the standard part. But here are some basic CLR test cycles for plastics, coatings, and textiles, and ASTM G155 general. All right, now let's have a look at a couple of examples from literature. The first example is for an automotive base coat or clear coat material, base coat clear coat material running at what would be considered pretty standard laboratory test conditions for an auto application in a xenon arc instrument. Note that this study is quite extensive, reviewing data from over 22 years of studies, 22 years. For many tests and materials, we see xenon tests to often be in the range of about 4 to 6 times over Florida, and maybe close to double that for North Central Europe. So the 27x number versus Europe is really surprising based on a comparison of the solar radiation number. This is higher than the comparison of solar radiation. Example number 2 is also on coatings. Note that the test method is quite similar to the example number 1 with comparable radiance, black standard, and relative humidity set points. But note the acceleration factors to South Florida are 50% higher, 6 times compared to 4 times in the previous example. And the comparison to Central Europe was 20x, or about 25% slower than the previous example, but still much greater than the approximate doubling that we would expect if we only looked at radiant exposure in Florida and in Central Europe. About doubling. What's going on here? Example number 3, also on paints. This test method is actually the same as in the previous example, except that they had more frequent cycling here with a 17-minute light, 3-minute light with water spray, a simple 1/6 fraction of the more common 102/18 cycle in the previous slide. This time the acceleration rate compared to Florida was 50% faster than the previous example, but still over twice as fast as the example in the first slide, the automotive paint and the 4x acceleration. Again. And here one of my favorites. These guys here have provided a very specific acceleration factor of 4.3 for the outdoor weathering specific to El Paso in Texas, which is a town in western Texas and right on the border between US and Mexico. El Paso has a transitional climate between a cold desert climate and a hot desert climate, with hot summers usually little humidity and mild dry winters. The acceleration here falls in that 4 to 6x range, predicted by radiant exposure equivalence. Since these geotextile materials that you see here on the picture, they are usually dark, they would be close to the black panel temperature and in a dry climate probably not very sensitive to moisture. The fact that these materials are polyolefin-based polymers also means they are relatively moisture insensitive. So in this case, the UV radiant energy dose is probably the major degradation factor, and this would be consistent with the data. But the widely varying and sometimes surprising acceleration factors in some of the previous slides says there is something more to degradation and acceleration than just radiant energy. This may be due to temperature or moisture effects or even something else. Maybe trivial for some of you, but it makes a lot of sense to look at these data to get a free and clear and fresh mind. From the previous examples, we can see that first, the experimental acceleration factors can differ significantly from those calculated from radiant energy equivalence and time compression in the lab exposures. Second, there is no universal acceleration factor. The factors are highly specific for both change in properties measured as well as the material chemistry and also for the specific auto and accelerated tests used. As I told you before, if you only do quick calculations based on radiant exposure, you neglect the material in total, and the material is the key factor you are interested in when you are doing degradation study. True acceleration factors must, and I repeat that, must be experimentally determined by using the auto and accelerated test data for the specific materials and the specific laboratory test and the specific auto location with a specific sample tilt and orientation, etc., etc. This means you need the real-time auto exposures and climates interest to determine acceleration factors. Always do outdoor exposures to complement your laboratory method, always. These are just values, real acceleration factors, and calculated. So here's a list of average outer annual radiant exposure values just for your reference, and the associated exposure times in hours here in the instrument if it runs at 60 watt per square meter with no dark phase. And these are the time factors or acceleration factors you can calculate from that, with all due disclaimers and cautions, etc. So the maximum acceleration you can reach by compressing the radiation time is limited, below 10. What if you don't have time for that? Can't you accelerate more? Yes, you can. You can by intensification. And here you have a couple of options. I will go through all of those or most of those as listed here below. Let's first look what intensification means. It's through overstress. That is increasing a stress parameter such as solar irradiance, in this case here, or temperature, to higher levels than what would occur outdoors. What this means is that rather than conducting a test at near maximum or maximum levels, you run it higher than maximum levels. One example of this type of acceleration would be the Fresnel reflecting devices in Phoenix, Arizona. We call them M-Aqua, where we use highly reflective mirrors to focus several sun equivalents onto one single target board, at least in the UV and low wavelength visible range. And this is a very established method and works quite well. Of course, it is also possible to both accelerate through time compression as well as through overstress. Of course, you eliminate nights and dark times, and you overstress, and then you get even more acceleration. Modern thin arc instruments and also fluorescent UV devices do have the ability, and various test methods take advantage of that and allow irradiance higher than maximum irradiance, usually up to 3 sun level, which is 180 watt per square meter in the UV between 300 and 400 nanometers. Just realize that there are practical as well as scientific limits to the amount of overstress we can use without affecting the correlation. The same is true with time compression by eliminating chemical processes that occur in the dark, as well as eliminating temperature cycling and its effect. So be careful. The higher the acceleration factor, the higher the risk for non-correlation. Well, take this chicken egg, for example. Many of you may know that. If I take that egg and expose it for 21 days under a mother hen at a temperature of 37 degrees Celsius, at the end of that time, I'll have a baby chick. But if I try to accelerate by exposing the egg for about 4 minutes at 175 degrees Celsius, the result is not what you expect. And this is exactly the same with your samples. So what can I do? What can you do? Well, let's look at each of the 3 primary weather factors. In terms of the radiation, when we think of exposing the material to shorter wavelengths of higher energy UV radiation. We have covered this in detail in other webinars, but we'll now see again that this is a very, very bad idea. Intensification by higher energy radiation, UVB. UVB 330 bulbs, as used in fluorescent UV devices, were the original lamps used for those exposures. This dates back to an earlier testing philosophy that if a material passes this test, sometimes referred to as the bigger hammer approach, it could not fail in normal sunlight. But this is past. However, one must be careful about the possibility of unnatural degradation. In some cases, the photochemistry can be so altered that the product passes the test but fails in normal sunlight. This happens with the first, or happened with the first automotive base coat clear coat paint system failures, a very expensive learning experience. The primary fluorescent UV standards, as shown in blue here at the bottom, 4892, ACMG 151, these are the general standards, and 154 and 4892 part 3, ISO 16474 part 3 for paints and coatings. These are the fluorescent standards. They specifically caution that UVB 330 lamps should not be used for weathering purposes. You see the 340 lamp here is much better in the solar cut-on region than the unrealistic radiation 330 lamp. So that you believe that, let's have a look at an example. In the graph on the left, the Florida exposure shows that material B, is the red one, shows a greater change in optical density than material A in blue. And this same change was essentially replicated in properly filtered xenon arc. Here, it looks very similar, but look at the time. This is 20,000 hours, this is 4,000 hours. This is an accelerated test, but the weathering behavior of these of this PVC here is very similar between materials A and B. And now look at the data from fluorescent UVB. What you see is there's a reversal in ranking when exposing the material to UVB, fluorescent UV. In short, do different tests in daylight, get a different result. Another example here is a comparison of UV fluorescent 313 with the low wavelength UV, and the more realistic 340 nanometer lamps, which I just showed you is a much better approximation of the solar cut-on region. It's for outdoor, for delta E, color change, the green one here, of 9 formulations of polyester coatings. Note that this is not a time series. It's not 1, 2, 3, 4, 5 hours. It's not a time curve. These are the different samples. Sample number 5, 7, 4, 3, 6, 2, 1, 9, 8 of these brown polyester coatings, different polyester coatings with brown color. And they are in order of stability. Yeah? Moving from left to right, the coatings are in decreasing performance. So these are the best and these are the worst, because this is the pass-fail line here. Delta E, pass-fail line, and you see they are these samples are in order of their performance. The outdoor data is green, the UVA 340 is blue, and the UVB 313, high energy, low wavelength photon UV fluorescent lamps, is in violet here, in pink. And now look at the data. Only coating number 1 produces the same magnitude of change. The UVB 313 lamps in pink produces completely different rankings and magnitudes. The 2 worst performing coatings in the outdoor, these 2 here, they are actually the best in the UVB 313 test. These 2, that's not good. Also coatings number 4 and 6, 4 and 6, which were very good performers outdoors. Here you see, outdoors good performers. They are ranked being the worst in the UVB 313 test. I think that should do it. Yeah, for UV fluorescent, I think you get my point. Don't use UVB 313 tests if you don't really very well know what you are doing. For certain tests that may work well, but you need to know what you are doing. Not only in fluorescent UV, but also in xenon instruments, filter systems are available that provide lower wavelength radiation than existing in solar UV irradiance on Earth's surface. The key example is the so-called extended UV filter system specified in automotive standards. Some of you probably know SAE-J 2527. That was formerly SAE-J 1960. Even the historically and still most frequently used xenon daylight filter system, Boro-Boro, it's borosilicate inner and outer filters in the thermometer. That's what that means. Provides a small amount of high energy photons not present in sunlight, which may cause differences in photochemical response for sensitive materials. But here you have the extended UV, which is a completely different world. This is from a study where the BASF reference clear code was used in a xenon instrument to assess differences in UV cut-on. What the researchers did, they used different UV cut-on filters and researched the crack formation. And the crack formation appeared at different times using the same moisture cycle for the different cut-on filters, 1, 2, 3, and 4. When filters with a short UV cut-on were employed, the cracking appeared rather quickly, whereas it took longer for cracking to form when longer wavelength UV filters were employed. Maybe trivial, but in practice, this is sometimes not taken seriously enough. A few years ago, or many years ago, I should say, the consortium started to optimize the UV cut-on for xenon laboratory testing. The result was what we call white light, or called white light back then, white light filter system, which has been introduced into ASTM 7968, the standard on transportation coatings. Both filter systems, bright light and the legacy filter bright light is here into that corridor. These are the extended ones. This is the legacy Boro. So both bright light and legacy are currently specified by ISO and ASTM, now in a new terminology as daylight type 1 for the legacy system and daylight type 2 for the bright light. We have a blog on our website, and Florian Pfeil, one of my colleagues who is one of the, let's say the most experienced expert in weather applications in our company, he wrote a short blog article on that. Just check that out. He's explaining the status. The slide here shows preparatory research to ASTM 7968, done mainly by Ford, supported by Atlas, of course, with the M-Aqua, etc., and the instruments. And that was presented by Mark Nichols of Ford in 2008 at the ATCAE, the Atlas Technical Conference on Accelerated Aging and Amelioration in Oxford, UK. It's quite old, but that was the kickoff of development of ASTM 7968. Accumulation of photooxidation products, it's shown here. Ratio with pass FTIR and outdoor and accelerated weathering was the basis of that. I don't go into specifics. This paper explains that there's also more published on that. These infrared bands, they change with weathering, and if you determine the ratio of different bands here, AB versus CD, you get an indication about the progress of weathering. Let's now have a look into the level of spectral irradiance. Many standards actually allow higher irradiance level, as I said already. Increasing the irradiance level is a common method. We do this already with the Fresnel reflecting devices, M-Aqua or ultra-accelerated MR test devices, described in part 2 of our webinar series on fundamentals of weathering. I'll just close the door. But running tests at both increased irradiance and increased temperature, however, is quite uncommon. The reason being that it generally leads to poor correlation as we start to throw the natural balance of the stress factors out of normal. So with irradiance intensification, we now need to talk a little bit more about the law of reciprocity, but I don't really like law. Law is not good. I like better principle or concept. Law is, it's too absolute. It's a principle or concept. This principle of reciprocity refers to running a test with higher irradiance than normal or induced normal conditions or induced conditions for a shorter time, but to the same radiant exposure of a natural exposure at normal irradiance for a longer period of time, and asking, are the results the same? To put it simply, can I get the same result in half the time by exposing my material to twice the irradiance, or in a third of the time with 3 times the irradiance, etc. Or even simpler, in even simpler words, to 2 photons of the same energy to exactly twice damage than 1 photon. Usually the law or the principle or the concept of reciprocity is reasonably valid for the photochemical initiation if other parameters like temperature are reasonable. However, the degree of this reasonableness varies, as strict reciprocity obedience is usually the exception. And this can result from several factors. While photons initiate photochemical degradation, much of the damage actually results from secondary reactions, usually involving free radicals, and these reactions are mostly driven by temperature and not by photons. Moisture control can become difficult, especially at high irradiance levels, which can affect specimen temperature, moisture absorption, desorption rate. Also, oxygen diffusion and availability in the sample matrix is a key factor in determining polymer degradation, and this cannot be accelerated adequately. And there are some dark time reactions sometimes for certain polymers that can't be photoaccelerated. These are only some of the reasons why reciprocity mostly doesn't hold true. But there is a technical way to find out if it works or not. ISO Technical Specification 19022 defines a process by which reciprocity can be validated. It's a relatively simple four-step process. First, test at lowest irradiance level, then test at increased irradiance levels. Here you see 55, 87, 100, 540, different irradiance levels. Then plot the test results as a function of radiant exposure and not as a function of time. And then all these points fall together to one straight line in this case here. Calculate the deviations from a fit of the data, meaning determine the Pearson correlation coefficient. And as you see here, it's excellent, can't be better. Pearson correlation coefficient is excellent. So for this material, for the orbit, orange weathering reference material here, it's a specific reference material in test alpha. That study showed that for this material, it worked very well. Another example, a bright yellow textile for safety garments. This time, two irradiance levels were used at 1x 42 and 2x 84 watt per square meter. Again, when the color change was plotted against radiant exposure, the reciprocity was very good, as shown by the linearity of the graph. The same procedure also works for materials where the property change does not linearly depend on time and radiant exposure. It doesn't have to be a linear curve. This is demonstrated in a study of two polyurethanes, PU1 blue, a foam, and PU2 pink, a woven fabric with a woven fabric behind, exposed in a test alpha at different irradiance levels according to ISO 105P06, the so-called hot light fastness test that doesn't have any rain cycle in it. You see, it also works well. You put these, this is time, if you plot that to radiant exposure in the UV, you also get these not into a straight line, but into one curve that you can fit, that you can fit. Here's a fourth example, this time for two different types of automotive interior textiles. Test 1 uses a relatively normal irradiance level of 47 watt per square meter, and test 2 3 times the irradiance, 141 watt per square meter. As you can see from the graph, the reciprocity was quite good. Now, one thing to note here. My parameter of interest in all these cases was color change, which is primarily a result of photochemical reaction which destroys the colorant. And these reactions tend to primarily be photon dependent. When you get into physical parameters such as cracking, adhesion loss, or tensile strength, which are often a combination of UV exposure combined with temperature and/or moisture cycling, the law of reciprocity likely will not be followed quite as well, because there are a lot of non-photon reactions occurring in polymer degradation. Important to keep in mind. The law of reciprocity may not always be valid. Here is an example for that, showing that diffusion may play a major role and distort reciprocity. We have oxygen and we have air with nitrogen plus oxygen, and we get completely different curves here. That was increased irradiance. Now let's have a look at temperature. For temperatures, we can possibly raise the temperature to higher levels in an effort to increase degradation rates, especially for physical degradation mechanisms. We can run tests that employ temperature cycling. A rule of thumb in basic chemistry class is that reaction rate doubles for 10 degrees Celsius rise in temperature. Rule of thumb. However, that only applies to some specific chemistry in solutions and is not true for the solid state materials we mostly deal with. The rule is derived from the more general Arrhenius equation, where K is the rate of the chemical reaction. What is shown here is not the Arrhenius equation. What is shown here is what we call the modified Arrhenius equation with an irradiance factor where the alpha, the exponent alpha, characterizes the reciprocity. If it is 1, the law of reciprocity is open. It's a material-specific coefficient. I won't go into details of that. This is topic of other webinars, but I want to point out that there are two important terms here regarding the rate of chemical reaction. The first, the activation energy, EA, activation energy, circled in red. This is the energy that must be put into the system for a chemical reaction to occur, because you have to go over that energy mountain, like needing a spark to ignite an explosive, which is nothing else than a rapid oxidation reaction. The second is the temperature, circled in blue. With low activation barriers, there are many molecules with enough energy to overcome this barrier, so the reaction is going fast anyway, and an increase in temperature has a small effect. An increase in temperature increases the amount of molecules with higher energy, translation energy or vibration energy. More molecules are able to overcome higher activation barriers. Thus, this has a big effect on reactions with high activation energies. This is not an on-off mechanism. Of course, it is related to the probability distribution of a molecule having a high enough energy to react, but that's an advanced topic. Only a little bit on that. Here you have this distribution. All but purely photolytic or photon-dependent reaction rates increase with temperature. The activation energy is a material-dependent property. It is the amount of energy that must be put, I mentioned that already, to overcome this barrier. And a high activation energy, not many molecules, this is a high activation energy, not many molecules have enough energy to react. If the activation energy is lower, then you have a bigger portion of molecules that have the enough kinetic energy. And then if you change the temperature here, you can actually influence that a lot. This is a new temperature distribution for a higher temperature T2. But I do not want to go too much into detail here. There's some activation energies, delta T's here. These are activation energies plotted, and this is gloss loss, and here photooxidation. That would a little bit too far if I go into too much detail here. It can change dramatically with activation energy. This is the message here. Not all Rankine reversals are the result of poor sunlight simulation, as discussed in the last paragraph. The reaction rate of photochemical degradation processes depends on a number of different factors, including effective irradiance and temperature, and the particular material sensitivity to the irradiance and temperature. And finally, the property change. Here we see the influence of temperature and degradation rates of different materials. Note this graph that the exposure of 3 different textile fibers was conducted with fluorescent UV lamps at 30 Celsius and 30 relative humidity. And here you have the same at 60 Celsius and 30% relative humidity. You see, reversal of ranking just due to increase of temperature. Now we combine the acceleration factor with a modified Arrhenius equation and get this nice formula that we are using a lot in modeling. This is the acceleration factor, which is the acceleration factor is the product of 2 independent acceleration factors, one regarding temperature, one regarding radiation. R here is radiation. And here you have the radiation and the temperature terms, which is the quotient, the ratio of the chemical reaction rates. And this simple product here is caused by, actually, if you go down into specifics, by the Frank-Compton principle, actually, which says that the photophysical steps are independent from temperature because they are running on completely different time scales. And translation vibration seems to be frozen when you are looking at a transition of energy in the electronic states of the molecule or the energy levels. Depending on reference temperature and material properties, the theoretical acceleration factor can significantly vary between different exposures. Incorrect estimation of sample temperature can lead to misinterpretation. Measuring the correct sample temperature should facilitate the comparison between different exposures. Another reason why conducting tests at higher than maximum induced temperature can be a problem is the fact that the material may approach the range of the glass transition temperature. This is the temperature where a polymer changes from a hard glassy state to a more rubbery state. Both states have different physical properties and therefore weathering behaviors, different diffusion coefficients, migration is different, etc., etc. The problem is that for some polymers, especially coatings, the TG of these systems is often quite near the typical black panel or specimen temperatures. And this can lead to erroneous interpretation, degradation rates, if you are not aware of that. This is just examples of different glass transition temperatures taken from the PVC handbook here, from the literature. 20 to 30 years ago, clear coats based on acrylic melamine systems were very popular, and these systems showed weaknesses in cracking behavior and stability against acids. This weathering study here shows that degradation of acrylic melamine coatings is 6 times higher at 80 Celsius than at 7 Celsius, instead of the rule of thumb of 2. At 80 Celsius, only 1/6 of the UV radiant energy is required for 25% loss than at 70%. Reason, the TG is between 70 and 80. For acrylic urethane systems, this is different. They are reacting slower, 1.4, than the rule of thumb of 2. Mind TG. Well, this can be very important. For temperature, we can raise the temperature to higher levels, but we also can employ cycling. According to the Coffin-Manson model, the thermomechanical degradation processes are based on the amplitude of the applied stresses, which here means the temperature range of thermocycling, delta A, TA and delta TU. A is accelerated, U is in use environment. And these are the number of cycles to failure. The Norris-Landsberg model estimates an acceleration factor, AF Norris-Landsberg, by multiplying the Coffin-Manson amplitude with a frequency term and the Arrhenius temperature term with temperature max in both environments, accelerated and induced. This slide deck here that you will be sent, that you will get, includes 2 more slides showing an application and a calculation example, but this would be would lead too far for today for this 1 hour presentation here. So I leave it out here. I just wanted to mention the names, Norris Landsberg and Coffin-Manson, and those of you who are interested in that, just Google it. Wikipedia probably gives you enough information to get a good idea. If you want to dive deeper, then you can check scientific literature on that as well, or textbooks. Now let's have a look at moisture. What can I do with moisture? Well, as I already mentioned, the first generation of clear coats 20 to 30 years ago were based on acrylic melamine systems. Investigations of clear coat systems were particularly important back then because they had weaknesses, first and foremost cracking, but also acid resistance. Weathering test methods were developed 20 to 30 years ago, first only in a climate chamber with water, without irradiance. Theoretically, cracks are generated when the humidity cycle has such a large amplitude to exceed the tensile strength after a certain point. Here in the trial, it is not reached in this one here. No, this amplitude is not enough. No cracks as expected. But now the amplitude is increased. The acrylic melamine systems crack after 2000 hours. Water penetrates deeper, the tension is higher than tensile strength. Formation of cracks is observed. The consequences for the paint manufacturers back then was development of clear coat systems with lower TGs and higher tensile strengths. Why? Higher tensile strengths to stay out of the critical conditions, and lower TG at about 20 Celsius to compensate mechanical tensions by swelling and contraction in the rubbery state above the glass transition temperature, which also avoids cracks. Modern 2K PUR systems are very good in this respect. Plus, acid-resistant PUR groups avoid damage by acid rain. So here are some of the big takeaways from this seminar. Most standards are based on time conversion and use parameters within natural limits. A compromise must be made between correlation and acceleration. The closer to nature, the more likely it will correlate. For intensification, carefully consider test conditions and material-specific sensitivities. No black box approach. Look at the materials if you're doing intensification. Options for intensification: short wavelength radiation typically does not work. Increased irradiance can work if law of reciprocity applies, and increased temperature can work if the glass transition temperature allows. So you should be always above or below. You should not cross it, or you should not have a different glass, a different state in test than you have outdoors. I hope you got that message in these slides. Acceleration factor of 10 or higher are extremely material and environment specific. Be careful. Be very careful. Okay, I'm coming close to the end of today. That was acceleration. The next will be correlation. I'm not sure when this will be presented, this week, next week. I'm not 100% sure. You should check out our calendar. Here is the overview about our knowledge resources. Check out the Knowledge Center on the Atlas website. We have a blog here, Atlas Weathering blog, calendars, 3 calendars, also of trade shows, but also on future seminars. We have technical guides, technical documents, a library ordered by topics like textile, coatings, technology, standards, etc. We have recorded online seminars, a huge list of them. We have weather summary reports that you can download for free. So this is a plethora of knowledge, of a knowledge resource for weathering. This is just upcoming online seminars. Right now we are somewhere, I'm not sure where we are. This is maybe September. These are all dates. I'm sorry. But the calendar looks like that for until March, April. You can check that out, and also the emails you get with the direct registration links. And with this, I would thank you for your attention. I will have a brief look if there are questions. Yes. How to choose, one question, how to choose between UVA 340, UVA 351 lamps to study the degradation of microplastic, PEPP, PA, and PET. Yeah, I have to tell you that the UVA 340 is a good approximation of the solar cut-on region, so the solar low wavelength region outdoors. UVA 351 lamps simulate the cut-on region of solar radiation through window glass, so inside cars or inside houses. So this is the difference between UVA 340 and UVA 351. The UVA 351 lamp has not really succeeded. It is a good lamp, but most tests are done with solar radiation outdoor simulation, but only in the lower wavelengths UV radiation. Here, no visible and no infrared. It's still fluorescent UV, but this is the difference. So if you are looking at outdoor conditions, you have to use a UVA 340. If you are looking at behind window glass, you have to use the UV 351 fluorescent lamps. So I don't see any more questions. Let me see. No, I don't see any more questions. So with this, I think we are right in time, 2 minutes after the hour. Thank you very much for participating. I hope it was a little bit interesting for you. You will get the slide deck. And if you have follow-up questions, please go ahead and send us a message and somebody will come. Thank you very much and have a great day, have a great evening, have a great night, and stay safe and well and healthy. Goodbye.